Talked by Greenbאום from the Haifa University, and will be ecological studies in the Mediterranean climate zone of Mount Carmel.
Thanks. I have to admit that I'm very excited because Aaron was my teacher for methodology, and I was always afraid of him. He was very strict, and I was always criticizing, always asking questions, so I always...
He's quiet now.
Exactly. So I was expecting always low marks from Aaron, but anyway, so... Okay, so this is a list of people, students and colleagues that are involved in the studies that I want to show a little bit in the Mediterranean climate of Mount Carmel. But the most important is, Yuval, who did his PhD with me after he did his master thesis with Aaron. So I will show some of his PhD dissertation here, and some other results of studies. Mount Carmel is an aquifers structural block, triangular shape, composed of aquapotential carbonate rocks, mainly limestone, yellowstone, chalk, and so on. In terms of rainfall, there's a big gradient from the coast to the top of the mountain. It's about 500 millimeters along the coast, increasing to more than 700 in the top of Mount Carmel, and the distance is about 12 or 13 kilometers. This is our research area. Aaron, it's 35 square kilometers, covered with vegetation. I studied in Jerusalem, and we studied in deserts and no vegetation, so it's very easy. But when we came to the north, we found out there's some problems related to thick soils and vegetation. So this is the catchment, and it's mostly about 60% covered with forests. Open areas. Then there's some agriculture, some traditional agriculture, about 50%, and about 25% of villages, Druze villages, Jewish villages, and so on. These are hydrometric stations that are located on the main wadis. Actually, built up in 1957, and in our university we renewed them in 2000. So we have quite a lot of data. If you can see, flood happens quite often in Aaron. As you can see here, there are some floods from time to time, at least between 3 and 5 floods a year. But this is a very typical rainstorm that occurred in December 2001. It's a very typical winter with rainstorm coming from the west. In the first day, this is the first day, this is a cumulative radar image of the first day, in which about 50 to 70 millimeters of rain. We had about between 50 and 70 millimeters of rain. In total, close to 160. And this hydrograph is the product, or it's partly reconstructed hydrograph is the product of this rainstorm. And as you can see, the first day, which I showed in the image before, was producing this flow. It's only about 3 to 4 cubic meters per second after the rainfall, about 50 to 70 millimeters. So it's a bit different than what I just showed. And then was a day of break, and another day in which another between 90 and 100 millimeters produced a high peak, about 17 cubic meters per second, which is very high for Mount Carmel. For the desert, it would be nothing. This is one of the stations in action. This is the pond, the upper first station near slot of the kibbutz of Oren, and this is a discharge of about 6 millimeters per second. It's pretty frequent flow in this area. And as you can see, even for small flows, sorry about that, even small flows, if you look on 2 stations, one after the other on the same channel, the upper station is the pond station, which summarizes about an area of about 80 square kilometers, whereas the bridge station summarizes an area of about 25 kilometers. This is a very typical picture that the discharge in the lower station is higher. This is a very typical picture in the Mount Carmel, whereas in the desert we find many times that the discharge is decreasing downstream. I can skip this one, and there are some results that just in order to get to know the system. So flow starts only after 180 to 150 millimeters, or cumulative rainfall of about 120 to 150 millimeters. During the winter, it can start earlier, after 50 to 70 millimeters. The flow upstream usually continues another 3 or 4 weeks because of drainage of the soils, big volume of soils, and also because of the increase in discharge of some of the springs upstream. And the largest flow that we ever know is historically is about 90 kilometers per second. So this is just a quick recognition before I start my talk. Okay? So this was the introduction. Okay, and so Yuval's work, Yuval PhD was, we're sitting here, was oriented to understand the recharge processes of the tunnel aquifer. So it's kind of the connection between what's going on top of the surface to the underwater. And he installed he added a lot of monitoring systems to the existing systems. We had 9 gauging stations of rainfall, and we had FDR and TDRs for the soils, to understand the water content in the soils. 3 hydrometric stations. We monitored 15 cave drips, 7 perch springs, and 6 drillings of the regional aquifer. This is additional contribution from Makkorot, who has about 6 wells in the Carmel aquifer. So I will concentrate on several sites, especially on in sites where we used the tracer method, mainly urine and aftermath, which was pretty much new, although the method is very old. The application here in aquifer with drinking water was not very simple, but we made it. And here is a cave, which is located in the northern rim of Mount Carmel, the main channel. This is the surface, and the cave is about 20 meters below the surface. This is the way it looks inside. And it's an active cave with dripping skeletons, and it's about 20 meters long. And we try to understand how long it will take water to penetrate from the surface into the cave, which is the present battle zone, of course. And sorry about this. Oh, the main picture is gone. Okay, so here it is. So Yuval took a tracer, urine tracer, just put it on the top and go skip one back. Sorry about that. This is the surface and this is the cave. Okay? We assume that some of the water into the dripping comes from here. This is the surface. This is the way the surface looked from pictures in the three sites. And this is a place where Ivan has installed a urinary tracer. We just dig a hole, a pit, down to the rock. It's about a meter deep. We installed the tracer and then covered it and waited for a storm. We had the prediction, and then after several hours, we got the dripping turning into rain. So that means that the urine passed all the way from the surface to the cave, 28 meters. Of course, we collected the urine. This is a rain gauge that Yuval installed, or several rain gauges to collect the water and monitor the dripping rate, which is actually the discharge of the drip, and see whether there are changes in the dripping rate, and also, of course, the chemistry and the pH and the conductivity and anything you would want to know about the water. So this is the hypergraph of one of the skeletons in relation to the daily rainfall in bars, opposite bars, and you can see there are some peaks related or maybe correlated to rain spells and some dry spells related to a decrease in the discharge. This is probably understandable. If we add the information of the tracer, and we look at the injection time versus the breakthrough time, we can see that the difference is about 75 hours. So in 75 hours, the tracer moved down 28 meters. You can calculate the rate, and you plug in it, and it's about 41 centimeters an hour. So if you always ask yourself, how quick is the water penetration into the water zone of the aquifer? So this gives you kind of a number. It was interesting to see this peak that had no urine at all. And our idea was that the new water that came by the new rainfall with the uranium just pushed down, kind of a piston bottle, pushed down in all the water that was still in the cave, still in the track of the skeleton, and that's why the first peak doesn't contain any uranium, and all the rest do contain and are pretty much according to the discharge. Just an average rate. This is the maximum rate. This is an average rate of water movement through the body zone in that area. I'll skip this one because of shortage of time. Also, we did some calculation as to, or Yuval tried to using hypergraph separation to separate between event water, the new water that comes, to the old water. We did it using a two-component n-dimensional analysis of chloride concentration. We know the input, which is the concentration of the rainfall. It's about between, I would say, 10 to 25 or to 30 milligrams chloride per liter. Pretty salty because Mount Carmel is very close to the sea. And so we know the input and we knew the output by measuring the dripping, the concentration of the dripping. So Yuval made some calculations to show the amount of new water, which is the recharge, into the dripping water. This is pretty high values because what he did is just sorting the types of dripping into the three types, or the main three types. It's what he called a post-storm, which is responding only to storms of water and is dry when there's no rain. There are seasonal that start in the seasonal drips that start in the autumn and finishes in the, let's say, in the spring, and there are perennial that, you know, that drip all year round. So this type is, of course, a post-storm response and a post-storm recharge proportion to this spell of drips. Another, I do have still time, or I'm kicking me off? Okay, I will pay you later. So there was another experiment. We extended this experiment with a group of from the Freiburg Water Institute, with led by Jens Lange, and we did an experiment of rainfall simulation experiment on the top of the surface above the cave. It was a big operation because we had to bring water from the wells, some 100 and 150 meters to the top of the cliff. We got some help from the fire brigade of Haifa, which pumped the water from the wells and just pushed it up onto the surface. And here, this is the top of the surface. As you can see, an area of about 140 square meters. It got rainfall simulation, and this is the relation between the cave and the overtopping area that was got the rainfall. Okay, and this is the artificial rainstorms. One rainstorm was about 80 millimeters in 7 hours, and then on the next day, another rainstorm of 190 millimeters for 7 hours. Okay, so this is the rainfall distribution in two rainstorms. We used a lot of rainfall accumulators spread all over, and this is derived from these accumulators. And this is the reaction of two drips, a post-storm drip and a perennial drips. It's not very well designed. It's a paper from Jens Lange from 2010, but forgot to say, in the second storm, we used another tracer, bromide, to see the same process. Once the soil and the rock are full of water. Okay, so in the second day, bromide was installed also at the top, and the results that you see here, the pluses here, are the bromide concentrations. Okay, this is electric conductivity. Okay, this is the discharge. Okay, this is a perennial drip. This is a post-storm drip, and there's a difference in the behavior, of course, of these two storms. Of these two drips, you can see the scale here is much different. This is a very low scale, and this is a very high scale. And you can see this is the discharge of the post-storm drip, and this is the discharge, and this is the discharge of the perennial drip. So that big differences in the reaction and the bromide concentrations there. Have we go? 1 minute. Okay. I'll skip some data, and I'll introduce another interesting experiment in the lower part of Nahatoren, where Yvonne wanted to check the connection between flowing water in the channel to the regional aquifer, which is below, 100 meters below. Again, we installed, I think this time it was an afterlight. It's another tracer, but we can, give you the same idea. this is the section that, this is the location of the well. This is the installation or the application of the tracer, and this is the flood coming. It was installed, of course, 1 or 2 days before the flood was expected, and this is the breakthrough curve of the naphthenate within the well. Okay, so when this is the time where the tracer was applicated, and this is the time where the breakthrough of the naphthenate was found in the water of the well, and this is the time that took water to go from the channel, from the natural flow of the channel, down to the regional aquifer, 100 meters in 16 hours. You can calculate about 6 meters per hour. So this is a very important information. And the final idea was to calculate the recharge based on models, based on 2 models, and type of information that I just showed now. And just to get an overview, a short overview, I know it would be more expensive than I thought. And there are 2 models which Yuval used, chloride gas balance and an infiltration model, and in comparison to actual recharge as measured by pumpage of the water by Mekorot. And as you can see, this is the actual pumpage, and this is the predictions of both models, which is pretty good to our opinion. No, I will not show the conclusion because it's so clear that everybody understands. And thank you very much.
No question?
No question.
Okay, we have now a coffee break. Just want to tell you that after 3 more talks, we will have lunch. And then we convene here in 25 minutes.
כן.